Hey eager learners out there, welcome to Biotecnika channel and to today's video which is on Alpha Helix. Yes, I'm going to discuss this topic from Unit 1 which is very important not only from knowledge perspective but if you know its different aspects then you can solve many questions in not only CSIR net exam but in other competitive exams as well, because proteins is something which is asked in all life science competitive exams. So yes, we are going to look at some properties of alpha helix, something about dimension, what type of hydrogen bonding will be present, the different constraints which affect the stability of alpha helix, what are the factors, and the amino acid propensities. Propensity means possibility, which amino acid will stabilize the structure more, which amino acid will destabilize the structure more. So without further much delay, let's start with the properties. Linus Pauling in 1951 reported alpha helical structure. So why are these important? Because sometimes these are asked in questions about the historical names. So it's better that you know these concepts very well. This is the most common form of secondary structure. Now secondary structure, as we know, it is a folding of the peptide backbone. This is an alpha helix structure which you're seeing on the screen, and this is your polypeptide chain. As you know, polypeptide chains, these are consisting of some amino acids. These amino acids are arranged next to each other, and when this linear polypeptide chain, which is formed just after translation, once this will be folded in some patterns, those are what are called as secondary structures. Okay, we have beta sheet, we have turns, loops, reverse turns, and also this alpha helix. We have gamma turns, delta turns. Different sorts of backbone folding is what is secondary structure. In alpha helix, the peptide backbone is tightly wound around an imaginary axis. So this entire structure goes linear. You can see that if you have an imaginary axis going through the center, then this entire structure is as if it's a spring which is coiled around this central imaginary axis. Okay, that's why we are seeing that it is longitudinally drawn through the middle of the axis. Very important point, the orientation in proteins. We know that proteins have mostly L amino acids, right? Most proteins, they will contain L amino acids, that is the levorotatory form of the stereoisomer, enantiomers, and they will form mostly right-handed structure. Now what does right-handed mean? You can imagine the thumb rule, where if you are pointing the thumb on the top, then the fingers go in the right direction. So similarly, if you are facing the orientation of the helix to be on the top, then where is your helix going toward? You can see it is going towards the right. If you see from the top, the strand which is towards you, you can see a part of the strand which is at the back. You can see a part of the strand which is facing towards you. Now that strand is facing towards the right. It is pointing towards the right. That's why it is a right-handed structure. Now why left-handed structure you don't see? It's not viable because of steric hindrance. Okay, so L amino acids, they don't have a tendency to form the left-handed helix. Yes, in some cases they will form, but with some additional bonds. Originally they will not form. You all must be aware of phi and psi bonds, phi and psi angles. So these are the dihedral angles, and these in alpha helix, obviously dihedral angles will also be fixed, and those range in negative. Phi will also be negative, psi will also be negative. So if you have the Ramachandran plot, you can expect them to be present in this quadrant. Okay, so here we take the 0 degree, this side is plus 180, this side is also plus 180. Here we take as psi, here we take as phi. So negative psi means it will fall in this area, negative phi means it will fall in this area. So this is the quadrant which is occupied by this alpha helix. Now coming to the dimensions. So a typical alpha helix, as you can see that it is having some length. Now typical alpha helix will have length of around 30 Armstrongs. And this is what is called as one turn of the helix. Okay, Now one turn is mathematically referred to as 360 degree. If you look at the alpha helix from the top, then it will come to a circle like this. Like from here if you start and if you come here, total it will be 360 degree. Isn't it? Now in this 360 degree, if you look from the side, it is coming like that. So it's starting from here and it is ending till here. That's what is meant by one turn. Now what is the length of this one turn? Very important. It is 5.4 Armstrong. I hope all of you know that 1 meter is equal to 10 to the power minus 10 Armstrong. Okay. And it is also equal to 10 to the power minus 9 nanometer. So you can say 1 nanometer is equal to 10 Armstrong. You need to know this conversions, otherwise if they are asking questions in nanometer, you have to give the answer, then accordingly you should be able to convert. Okay, so this is 5.4 Armstrong, which is also called as the rise of the helix. There are some names and terminologies which are given, learn it over here. This is also called as the pitch of the helix. Pitch means that it is rise per turn. Okay, you can also write it as rise per turn is what is pitch of the helix. And as is written over here. And how many residues are present in this one turn? So you have 3.6 amino acids per turn, right? In this area, why 4 is not there, you may ask, but 4 is means 3.6 means the rest part, that is 0.4, it does not come accommodate in the previous turn, it accommodates in the next turn. So that's why the number comes to 3.6 residues. Now, what is the length of this part between two amino acids? So, if here you have one amino acid, here you have one amino acid, then what is the rise per residue? Or if we say rise per amino acid, okay? So, rise per residue or rise per amino acid, because this was rise per turn, right? So, if this entire length is 5.4 and there are 3.6 residues in this one turn, that means what will be rise per residue? It will be 5.4 divided by 3.6. Okay, so that's what gives you 1.5 Armstrong per amino acid. Right, it's not the physical length, but it is the length in the helix itself. Then you have helical twist. So we know that the entire turn is 360 degree. One turn is 360 degree. And in this one turn, how many residues are present? 3.6. That means the total angle 3.6 residues are present over here. So something like this is first residue, second residue, third residue, fourth residue will be here. So basically what is the angle between these two residues? It is nothing but 360 divided by 3.6. So the angle between two residue is 100 degree. That means one residue is rotated 100 degree with respect to the other one. So here is the first one, here is the second one, here is the third one. The fourth one is not in the same turn. It comes in the next turn. So fourth will be here, again 100 degree, fifth will be here, again 100 degree, sixth will be here. So that's what it goes like this. This is what is called as a helical wheel. The observation what you will see from the top, it is helical wheel. Where do you see the peptide planes? They are roughly parallel with the helix axis. Peptide plane forms between CO and NH. So as you can see, this is the peptide bond, right? So peptide bond, it is roughly parallel with the helix axis only. You can see here another peptide bond is given. So these are parallel with the helix axis. Where are the R groups or the side chains? Amino acids will have the side chains. So side chains generally they will protrude out. Okay, it will be up and above. They will protrude out, because if they are protruding towards the inside of the helix, they will create steric hindrance. And as I mentioned, the prototypical amino acid range of phi and psi angles are in both negative, roughly around somewhere minus 45 to 50 or minus 50 to 60, like that. And this side is the C terminal, this side is the N terminal. You must know all these details for understanding the alpha helical structure. Next details is about the hydrogen bonding. So how is the hydrogen bonding in alpha helix? To understand that, let's have a look at this picture first. Here we have some amino acids. This yellow blocks what you see, these are amino acids. How do you know? This is central carbon alpha. This is the R group, variable side chain, hydrogen, amino group and carboxyl group. Now we know in polypeptide chain, the carboxyl group of one amino acid is joined with the amino group of the next amino acid. So between two amino acid, between these two yellow blocks, what you can see is this is the peptide bond. So like that here also you have another peptide bond. Between all amino acids you have this peptide bonds. That means how many amino acids are there? This is the first, second, third, fourth, fifth, sixth, like that. Okay. Now we don't call it for 1, 2, 3, 4, 5, 6 because we don't know if this is the first residue of the polypeptide chain. It might be possible that the polypeptide chain is coming like this, then it is forming the alpha helix and then it is going. So even if you feel that this is the first residue of the alpha helix, it may not be the first residue of the polypeptide. Polypeptide numbering would have started from here. That's why if we write 1, 2, 3, 4, 5, 6, it is not proper. So in that case, what can we write? We have to consider this as ith amino acid, or we can say nth amino acid. So the next one will become what? I plus 1 amino acid or n plus 1. The next one will be I plus 2. Next one will be I plus 3, I plus 4, I plus 5. So actually, the I plus 5 is nothing but the sixth amino acid. This type of nomenclature you must know if you have to understand hydrogen bonding. Okay, in the secondary structures, you have to follow this pattern. Now, how is the hydrogen bonding done in alpha helix? See, there is a arrow going from here to here. Now, let's understand which are these groups. This is the CO group. Now, CO group belongs to which amino acid? It belongs to this amino acid. You see the box over here? So, the CO groups belongs to this amino acid. Now, what amino acid is this? ith. That's why we can say CO of ith amino acid is connecting to NH of, now which is this group? NH belongs to which one? This one. So it is I plus 4. Okay. So this is what is the hydrogen bonding. Very, very important question. Very, very important point for questions. CO of ith residue to NH of I plus 4th residue. What will be the next hydrogen bonding? Obviously, the next one will be from the next amino acid. That is from the CO group of I plus 1. So the next hydrogen bond will be after this. The next hydrogen bond will be CO of I plus 1 to NH of, now this also needs the same spacing. The spacing should be some 4 hydrogen bonds in between. So it cannot bind with any of these NH groups. Neither can it bind with NH group this side. It has to be in the same pattern. It has to bind with NH group somewhere over here. Okay. So that's where it will form with this one. Now this NH is what? The NH of I plus 5. So after this residue, you will have I plus 1 to I plus 5. Okay. After that, you will have I plus 2 to I plus 6. Like this, it will continue. That's why in a given helix of a given amino acid chain length, you can find out how many hydrogen bonds will stabilize that structure. Okay. Now, what is the length of hydrogen bond? We know the hydrogen bond consists of D, H and A. That is donor hydrogen and acceptor atoms, right? So here these are the acceptor atoms and these are the donor atoms. So actually donor attacks the acceptor, but we write like CO of I to NH plus to I plus 4 because of the numerical order. Okay, and they are 180 degree in plane. That means they are linear. As you can see the hydrogen bond in alpha helix, I showed you in this picture. So here you can see the length, the hydrogen bonds are linear. And in case your hydrogen bonds are linear, they are very strong structures. Okay, that means their strength of hydrogen bond is very strong. Fine. There are 13 atoms which are present in the backbone of one hydrogen bond. Now what does that mean? If we start numbering from here, okay, so if we write this as 1, 2, 3, only the atoms in the backbone, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. So you can see, ignoring the non-bonding atoms over here, only in the backbone, if you start from the CO group of I plus 1 and then continue till NH group of I plus 4, you are getting total 13 atoms. This is also a very important information, because of which alpha helix is also called as 413. That means the spacing is 4 amino acid residue apart, the hydrogen bond, and in one backbone of hydrogen bond there will be 13 atoms which are present. And the first 4 amino acids and last 4 amino acids, they will be only partially involved in hydrogen bond formation. So what does that mean? It means that this NH group, this one and this one, they cannot have hydrogen bond. Why? Because for them to form hydrogen bond, you need some CO group before them, that to 4 residue apart. But since this is the starting residue of alpha helix, they can't bond with any other CO group. That's why the first 4 NH bonds will not form hydrogen bond. The last 4 CO groups will not form hydrogen bond. So in case you are getting any question that, let's say you have a alpha helix residue of 10 amino acid residues. Okay, alpha helix of 10 amino acid residues. Then how many hydrogen bonds will be present? If you have to calculate this question, then what you need to do is, all you need to do is that first 4 will be having half of hydrogen bonds. Okay, last 4 will also be having half of hydrogen bonds, that is 7 to 10. Also they will have half hydrogen bond. And 5 and 6 in between, they will have complete 1-1 bonds. So 1, 2, half into 4 is 2, half into 4 is 2. So 1, 2, 3, 4, 5, 6. Answer is 6 hydrogen bonds. So whatever number you get, if you get 50 amino acid alpha helix, all you have to do is subtract -4. So in that you will find 46 hydrogen bond. Okay. So next, coming to the other properties, that is constraints affecting stability. So what constraints affect stability? Electrostatic repulsion or attraction between successive amino acid residues with charged groups. Peptide, the entire alpha helix, so this is your alpha helix, it has a dipole moment. You have a negative charge and a positive charge in the peptide bond. So actually peptide bond itself has a dipole moment. The CO side gets a partial negative charge, the NH side gets a partial positive charge. So in the alpha helix also, the C side end has a partial negative charge, the N terminal side has a partial positive charge. That's why oppositely charged amino acids will be preferred. So if you have the N terminal which is positive side, negative charged amino acids will be more stabilizing. If you have positive charged amino acid at N terminal, it will be destabilizing for the alpha helix. Okay, and the other way also goes for this consideration, that at the carboxyl terminal you have delta negative end. So here if you have positive charge groups, then it will be stable, but on the other hand, if you have negative charge groups here, it will be destabilizing. Okay, what else you need? The bulkiness of adjacent R groups. If from here also some big group is coming out side chain, from here also some big group is coming out side chain, so they will interact with each other and that will create a problem for the alpha helix to be stable. Also interaction between successive amino acid residue. If you have long stretches of negative charge amino acid, so these negative charge amino acids are creating repulsion between each other. Or else if you have any positive charge group, negative charge group here, positive charge group here, then they are acting as stabilizing forces over here. So as you can see, long stretches of similarly charged amino acid can create a problem. Even ionic or hydrophobic interaction between groups which is placed 3 to 4 residue apart. If you have a negative charge group here and 3 to 4 residue apart, if you have positive charge group, ultimately they will be facing each other. Interaction between amino acid residues at ends of helical segment and electric dipole inherent to the helix is what is important to have the constraints of stability. Now, what all amino acids can be present in this alpha helix? So you have 5 most common amino acids and unfavorable amino acids. Now 5 most common ones which are preferred are methionine, alanine, arginine, lysine and leucine. These can be comfortably present, but unfavorable amino acids you have proline and glycine. Now why proline can't be present in alpha helix? It's because the amino group does not have hydrogen bond to form hydrogen atom, because of which a kink or a bend is formed in the helix. Since proline peptide bond is just CON, it doesn't have the H group, because we know the proline side chain is connected with its own amino group, because of which the hydrogen is missing over here. And we know that in alpha helix, hydrogen bonding forms between CO group and amino group, that is NH group. So if NH is itself not there, then that hydrogen bond will be missing, because of which a kink or a bend is created in the alpha helix. Also, ring structure does not allow for 100-degree rotation. Another one which is not favored is glycine. So glycine is not favored because it is too flexible to stabilize the helical structure. As we know, glycine has only hydrogen in the side chain, right? So it's a very small amino acid, and because of which it is too flexible to be present in alpha helical structure. Serine, aspargine, aspartate. So the bulk and shape can destabilize helix if they are too close together in chain, because they have this polar groups OH or amide bond, which can also interact with each other and destabilize the structure. Threonine, valine and isoleucine, these are branched amino acids. Branched amino acids are also not favored, because you can well imagine from here if a branch is coming out, from here also another branch is coming out. So these branches can create steric hindrance. That's the reason why they are not allowed in the alpha helical structure. So that's it for your alpha helix. All very important points to keep in mind. Thank you very much for listening. Do let me know in the comment section if you like this video and what else you would want to understand from this unit.